All right, good morning, folks. Happy Monday. Another Monday back. 2 weeks left of online. That's it. We're back in person, which is awesome. This online is getting a little old, but it's the way it is. So today we're going to talk about weld profiles. So that's the shape of our weld, how that can affect the outcome of a weld, the end result, the weld strength, the weld integrity, and the detrimental effects it can have on the base metal or associated pieces connected to the base metal. So we're going to get into it a little bit of the little deeper dive into welding. It's not just about how to put down that weld, but it's about how to put down that weld properly. So what we're going to do is we're going to share a slideshow with you guys today. The slideshow is going to go over different shapes of profiles, how to determine what's going to be the best profile for the weld. It's going to get you thinking about what does that weld do, how to shape it, and it's going to have lots of drawings with stress lines flowing through it, and it's going to show you how the stress flows through certain structures, and that'll kind of hopefully indicate to you guys how those welds should be shaped. And then we'll look at some examples of good and some examples of bad and some examples of what we'd like to see. So that's that. All right. So what we're going to do is we are going to share our screen this morning. Share that. Then we're going to pop up to weld profiles. And we're going to present this. All right, so FAB 20, your intermediate level, and we're talking about weld profiles. So let's move on here. So right off the bat, what we're doing here is what's called a nick break test. This falls under the category of destructive testing methods. So what they often do is they will cut a notch right through the top of your weld, right through the bottom of your weld. And then what they're going to do is they're going to take a press ram and they're going to see how much force it takes to split your weld in half. There's a bunch of different tests we can do. I don't like to do destructive tests in here. Firstly, I don't have the equipment for it. And to create the equipment, it will cost some money, but also if we're building this equipment, we don't have the guaranteed safety that a lot of these pre-manufactured pieces have gone through the testing for. So it's a lot of a safety issue too. We do cut up some welds and we do etch them with some acid, some nitric acid. But other than that, we don't get too destructive as far as destructive testing. So stress flow lines here, what this drawing is indicating is just showing a length of material and how the stress flows through it. The lines are pretty evenly spaced, run parallel to the general outline of the object being stressed. Stress flow lines are indicated by the dotted lines here. So this piece isn't seeing much stress at all, and everything is flowing. It's all straight. But then we start, welding pieces together. We've got hard 90-degree corners. We got 45 degrees. We've got, load bearing, wind bearing, all sorts of forces on these pieces we're welding. So we're going to learn kind of how the stress works with those pieces. So a notch effect, guys, is pretty much a hard transition point where you do not get the smooth flow of stress lines. Stress lines are going to be either grouped together quite tightly, bunched or interrupted, or they will make a very sharp turn. In the welding world, it's not a good thing to have this type of effect. Often if the machine is subject to impact or vibration, you're going to see a crack develop there. So that's why if you weld with, a big convex cap, the stress flow lines are going to flow across the face of the surface, hit the edge of the cap, turn, move through the cap, come down, turn, and then move back to the plate. Kind of similar to what we see here in this middle graph here with the notch effect, how everything makes a hard turn down. This would be likely to fail, and it would start cracking right here and probably crack just on the outside of that weld. And it would fail there. That's not something we want to have. We never want to have welds fail. Well, I guess technically these welds wouldn't have failed. It would be the steel around it as a result of the welding. That is something we need to avoid as well. We don't want to be responsible for damage to equipment or machinery by some poor welding practices. So here, example A is an attempt at tapering this out to get a bit more flow of the stress lines. Now they've done definitely some work here. You can see we still have a pretty hard transition here at the bottom, and these inside notches are going to be where the stress is going to cause a fracture. And then this would then fracture right on the outside of this weld, probably down along the weld, and then those pieces would break. This one here, we can see there is no attempt to bevel this back, no attempt to make it flow with welding. It's just there was a single bevel here. They threw a ton of weld in it, and they have this hard transition. So a couple options here. We can taper it back. See here's taper back on a 3-to-1 ratio. This gives us stress lines nice flow opportunities. There's no hard bunching, no hard transitions. There is a bit of a harder transition right here, but I think that's just due to the animation. This middle one, we can work this in 2 different ways. We can add additional weld if we have the ability to help taper this out a little bit, or we can simply grind this back on that 3-to-1 to help create that, that better effect with the weld. Oh, okay, let's move past this one. No, this one. Okay, here we go. So this here is kind of showing the connection of 2 pieces together. We have a smaller bar connected to a bigger bar, and you can weld them. This is basically just a straight butt weld. That can work. It can be done. If it is seeing stress and has some dynamic movement to it, that means, you know, seeing forces, compressive and stretching forces, then we want to taper it back. And we can see here, this example on the bottom, it's got that 3-to-1. So if I was to draw a line up here, put a 90-degree corner and then taper it back to here, this would be that 3-to-1 ratio that we just saw in right here in this last slide. So that's just doubled up. And really this here, the middle slide, is just an extreme example of this one right here. So this is how you taper stuff together. You'll often see this with pipe. You'll see reducers. You get elbows and reducers, long elbows, short elbows, conical reducers, concentric, off-centric reducers, lots of different things. But you'll always see on those when they taper them down, it's a nice gentle taper and we don't have a big hard transition. So this is how some notches can affect, or your welding profile can affect your welds. We see these, we're practicing with some of these plates. When we get back, we're going to be doing a lot of these type of lap welds. So if we stack another one on top of here, it would just look like your stair set that we weld. When we're doing this, we do get stress flowing through here. Generally, you have both of these welded if you can. It's not often that you can always get back to the other side, but in our classroom, we're able to. So we're going to be welding on both of these. The best thing to do here is to be very cognizant of what your profile looks like. So generally when we're doing flats and horizontals, it's not too big of a deal. But if we're looking at this from the top down, if this is the top, we're looking straight down, and this is a vertical weld. Vertical welds are often pretty prone, I guess the word would be, to having this belly in the middle of it. So we got to learn to control our profiles a little bit. That could be adjusting our amperage on our rod, maybe turning it down just a little bit so we have more control over it. Things like that. Basically keeping a shorter arc, keeping your arc tight into the plates. That'll help control this big belly on the front. Keeping that longer arc is going to allow that belly to fall out and get big. And then that changes the profile, creates something we don't want here. Here is a bit of a notch effect. It's done with a concave weld. This weld here could be created by dragging a downhand vertical weld down the joint. And it's not bad, it's smooth, it's got nice transitions. This one here is a little hard, but the weld size creates a lot of issue, because what happens is this plate is 3/8 of an inch wide and this plate is 3/8 of an inch wide. We want a weld with a 3/8 effective throat, so we don't pinch all those lines and bind them up right here. So if we got these lines a lot closer together here, that's going to cause that notch effect. That's where that break could happen. So in a weld like this, we got a 3/8 plate, 3/8 effective throat on the weld, 3/8 plate. We see nice flow, all the lines are even. So we don't want to create that pinch point right here. That's basically what we're looking to avoid. Any spot where those welds are going to be forced, or the stress lines are going to be forced together, that's going to be a place that may see some failure. And this kind of shows how gussets and corner braces affect stress and load distribution. So if we're building some sort of second level structure and we're putting posts underneath it, straight vertical post like this, if it's seeing a lot of movement, the stress lines will take a hard 90 and move left or right from the post. This could potentially have effects on the welds here and here. Generally, structures don't move that much, but if it's subject to a lot of wind, say here in Alberta, this may be something we would want to avoid. We want to add in gussets. So these are gussets. They aren't basically steel fins that go in here to weld them into place, and it helps distribute the force and the stress. And these here are what we call knee braces. This will get put in place and welded on all four sides. This will be the same material as this normally, or pretty close to it. You often see these out of a 4x4 piece of steel, square tubing. And you'll weld all four sides there, and that helps create some nice even flow and strengthens this joint itself. It gives a lot more stability and rigidity across the span. So it's a lot more likely to take stress better. Okay, so a couple things we're going to see when we get back. We talked about the stringers versus weaves padded plate that we're going to be doing. So this is a weld. This is a butt weld here, but this weld is weaved in. And a couple of things we see here is a crater notch at the front, or this is the back, sorry. They started here, they welded this way, and they didn't quite fill up the end. They yanked that rod out of there before it filled up. We can see that square wall right here, and we know there will be a square wall right here. That is going to be what we want to avoid. We don't want to have those square walls. We want to incorporate all this into the weld. We want the weld to come right to the end of the plate. Also, on the same thing, we want to start the weld at the end of the plate. We don't want to come in a 1/4 inch or anything like that. There's going to be a definite hard transition between this 90-degree square wall and this weld, and that's going to be a point of failure. I'm going to close the door, guys. I'll be right back. All right, so we're back. Above, on the top of this graph here, we see desirable fillet weld profiles. So the big thing we're looking for with this is what we see in the middle here. So we have 45-degree weld with equal legs. For the most part, it can be equal legs. It doesn't have to be, but when you see equal legs, it's usually a pretty good indicator that your weld is decent. And then we have here is a convex weld, but it's a larger convex weld, and it does have the equal leg effective throat on the inside. So we basically can hide this weld inside of here. We see there's a little extra here and here, but that actually can be quite helpful, this little extra bit. What it does is it helps create nice flowing lines for the stress. You're not seeing a hard corner or a notch effect. So if you have excessive undercut on one side of a weld, that can definitely cause notch effect. That's something we're trying to avoid. And here, this is decent. It's got the taper. So we see it's probably more like a 3-to-1 taper or a 2.5-to-1, whatever it might be. There's a little bit of excess weld there, but that doesn't really bother us. It doesn't really have an effect. So this is kind of a more tapered one. Here we have a little notation here, convexity C shall not exceed 0.05 of an inch. So, or 0.15 to 0.05 of an inch. So that's basically 1/8 of an inch, because 1/8 is 0.125. This is 0.15. This is a little bit more of an eighth of an inch. So we don't want to have big belly hanging out on our welds, right? So, oops, we're going to look right here. And what we have are a couple examples of some things that aren't the best in welds. So here we have on this left side right here, we have a multiple stringer fillet weld. Now it's probably 3 stringers went into that fillet weld. We'll have 1 on the inside, 2 on the outside. But what happens is right where this arrow's pointing, we got a big valley. And as we know, we're trying to avoid those valleys in our welds. We're trying to get those caps or the ridge points of our welds to meet up nicely, have a nice flow, and pretty much be blended in almost seamlessly. This valley here, that valley protrudes below the line for the throat of the weld. So if we're given, say an 8mm weld, and every weld on this page is represented by that 8mm. This one here with that little point being lower than that face line there, this weld would actually be smaller. It'd be more like a 7mm weld. And that can actually come back and bite you in the butt when you're doing some work. So you want to make sure that things are the proper size with the correct profile. Here, and what it looks like is this person is doing a horizontal weld. Maybe got a little too hot because we see what's happening here. Almost looks like what we see when we get undercut. We get a washout here and then a pile up at the bottom. That could be, multiple factors going into that one. Long arc length often creates stuff like that because your arc is heating up a bigger area, and then it heats up more of the material. It falls down and doesn't replace all the material that it cuts down. So keeping a shorter arc length, especially when we're arc welding, is going to give us much more controllable and predictable weld bead when we're laying that down. We back that rod out of there and we have that large electrical fan flapping around. Firstly, it's not concentrating its heat where it needs to. And when it does direct weld off the end of the rod, it could go in a number of different ways. So that could end up giving you things like spatter. We don't want spatter on our welds. It's a pain in the butt to clean off. So keeping that nice short arc length is going to give you a much more predictable weld profile. Here we can see we got that undercut, kind of an example off of this one. Now maybe that long arc length, they cut away all this material. The weld is the correct size, but we got a bunch of undercut right here, and that would crack right from that point through whatever piece it was, and that would be a horrible weld failure. Overlap. So, this edge is looking okay, but as we see, the weld is not of equal leg length. So it's a smaller size here than it is here. And that's not what we want, because we want to have an equal leg length if possible. Unless we're tapering back welds, then we want a 3:1 taper ratio. And here, insufficient leg. So they got the bottom leg out where it needs to be, but this top not built up enough. I often see this with the 10s and 20s. What happens is they'll point their rods pretty much on a downward angle, say 15, 20 degrees of layback, not much. And it's going to push that puddle down and wider this way. Whereas you come in at a 45-degree angle, it's going to push that puddle in and hold it up on the back wall. So this could easily be created by electrode manipulation. Acceptable butt weld profile. We're looking right here. What we see is R, and the R stands for reinforcement here. And it shall not exceed 1/8 of an inch. That goes for the cap and the root. So if your root's hanging down a 1/4 inch, that's going to be way too large. 1/8 is the maximum what we want. And there is a reason for that. So the reason for that is if you are welding a pipe and you have a root that's hanging down 1/4 inch the whole way around on the inside, what you're effectively doing is reducing the inside diameter of that pipe by 1/2 inch, because you're 1/4 inch on one side, 1/4 inch on the radius. You have to double that to get your diameter. You're effectively reducing that by 1/2 inch the whole way around. So you're creating a restriction inside the pipe for whatever flowing materials are in there. And then also what happens is as water flows, if you guys have ever looked at the river, you see water will be nice and flat, and then it'll hit a big rock in the middle, and you'll see those swirls on either side of it. That's a vortex or a vortices. And what happens is those vortices, as the material flows over it, it gets turning, it gets spinning, and then that material spins and wears against the inside of the pipe. So those vortices actually create weak points on the downstream side of those welds due to the turbulence it creates inside the pipe, and that's where pipe fails. It wouldn't be the weld that failed, it would be the wall of the pipe slightly downstream of that weld. So that is why we try and avoid that. We try and avoid any intrusion, major intrusion into the inside of the pipe. All right, and as you can see here, if we're doing examples, we got insufficient throat. It's not big enough. If we drew a line from plane to plane and plane to plane, we would see that this weld does not touch either of those ones in the middle. Here, it's too much, it's too big. This guy here, the weld looks great, except for the fact you got horrible undercut on either side, and this will shear or break on those ones. And overlap, you just got too much. You're going too far into each plate over here, too far over here, too far over here. I had a student come in the other day in my 30 level, and they had to catch up on a weld. They tried one, and they ended up very, very wide on it. And that would have been an example of overlap. So instead of being a maximum 1/8 from the edge of the weld, because if we're looking at this profile here, you don't want to come more than 1/8 into the plate on either side from the edge of your butt weld. Here, this is much farther than that. All right, so excessive convexity. We got this weld here, it looks more like an egg of some sorts, but what it's showing is this convex profile creates a horrible notch effect here, a horrible notch effect right here. Those are going to be failure points. And this will crack down through to here or across. This will do the same thing, and you might as well have not welded that at all. So that's all I got for you today, guys. That is it. That's the slideshow. Trying to keep it nice and short. And yeah, so hopefully this gives you an idea of what things should look like when you are creating your welds in class here. There are a bunch of, ways of doing it, a bunch of different situations that are going to call for different things. When I'm welding on things, like I've welded on cranes, I've welded on derricks of oil rigs and stuff like that. You don't want those big notchy welds. They see a lot of stress from hydraulics and cable systems and wind load and things like that. You need to have welds with the appropriate profile. And sometimes that means, adding a little bit extra to a weld to help create that smooth flow instead of that hard transition. So on welds, what I've done in the past is I've, welded a vertical weld uphand. And then in those corners, you get what could potentially develop into notches. So once you know this weld is in there good, now this I would definitely speak with whoever you're working for before doing it. But what I was doing is I was taking rods and starting at the top of my weld and going downhand in the corners to fill in the corners to create smooth transitions. Now, some employers will not want you to do that whatsoever. They want everything uphand. But in the case that I was working on, the welds were basically inspected, and then I changed the cap profiles at the end after the actual weld was inspected with additional weld. That's what I changed the cap profile with, a little additional weld to create more smooth flowing transitions. Every job's going to have its own special needs and whatever it is. Generally, you're going to be informed of all that by the foreman, the person who is calling you to do the work. There are some situations where you're going to have to make your own calls on things. So hopefully this helps educate you guys a little bit on what a good weld profile should look like and how to avoid failures due to poor profile on a weld. All right, so I have that is that for that today, guys. Let's see here. Awesome, I'm just gonna stop this recording.